Okay, off we go. So, new chapter today, going into chapter 7. The big sort of the big update that's coming in chapter 7 is we're going to sort of start moving into 3 dimensions. Right? So all of chapter 6 we've been doing 2-dimensional stuff. The fundamental theorem of line integrals does apply just as well in 3 dimensions as 2, but the point is you can think of it in 2 dimensions, and everything you need to know about it you can figure out in 2 dimensions. So effectively we were thinking in 2. Okay, so that's one of the big pieces of news. We're moving to R3. The other thing I want to mention here is a lot of 7.1 is pretty readable, actually, and it's pretty analogous to stuff that happened in 2 dimensions and that we've done previously. So I'm going to move pretty quickly through this. Of course, I'm sure you've noticed that we're behind schedule on the calendar, and today is going to be a day that we're actually going to make up for a lot of that. Because I'm just going to kind of wave my hands at a few things, point out a few critical points, and then we'll move on to where I can help you more, right? Where there's tougher ideas. Okay, so first of all, we're talking about the idea of a parametric surface is morally the same concept as a parametric curve. Parametric curve is a position as a function of one parameter. A parametric surface gives position as a function of 2 parameters. It's a big idea. Right? Now we've already seen an example of this back in section 1.5. We talked about how this construction right here will generate a plane. And the big idea is that S and T, your parameters here, right? So the things that you give let's make a better color choice. Position in terms of basically tell you this says how far to move in that direction, and this says how far to move in that direction from some agreed upon fixed starting point. Okay, so old news in some sense, right? And there's a bunch more examples. The book, again, has examples of here's a parameterization. What does it parameterize? And again, I'm going to do sort of the opposite version because I think more real world, when you need to parameterize something, the point is it doesn't come to you pre-parameterized. I think generating parameterizations is really important. So I'm going to focus on that. And for example, the graph parameterization, again, same basic idea. If you're looking at a graph, right, whatever are your input variables, let those be your parameters. It's the same basic idea. It's just that now there's 2 input variables, and there's therefore 2 parameters. Same basic idea. And notice, of course, when you plug that in, when you plug that in, then the equation, I wanted to change the color. The equation telling you the variable who's, that is the graph variable, tells you how to rewrite that in terms of the parameters. So, boom, it's the same basic idea. Again, you don't have to have solved already for it. You could take an equation and solve for one of the variables. And notice also, it doesn't have to be Z. And there's no alphabetical order magic here, right? So whatever variable. Same basic idea. Okay, and just like we saw with polar coordinates, likewise, you can kind of rip this off. Same basic idea for spherical coordinates or cylindrical coordinates. You just kind of have to sort of insert the conversion formulas. All right, so there's our spherical to rectangular conversion formulas. Again, old news, chapter 1. Okay. And notice, here we have what you might call a spherical graph, because I've solved for one of the spherical variables in terms of the other spherical variables. And, well, just as we did on the previous page, you kind of stick it in where it goes. And, oh my gosh, as required, we now have position as a function of 2 parameters. And here our parameters are phi and theta. Is everybody on board? Is everybody doing all right? Now, real quick, I do like to point out, I think this can be a little bit confusing. Hey, here we had 3 variables, x, y, and z, and we felt the need to rename, our parameters. I didn't want to use x and y as parameters here. I'm using s and t as parameters. How come I didn't do that over here? How come I didn't rename phi and theta as s and t? And you can, if you want to, go ahead. It's harmless. The main reason I do it here, though, is to avoid what I'm going to call confusion of variables. I remember it's a little uncomfortable if you use the same variable name for both inputs and outputs. And I think that would be a problem here because x, y, and z are the outputs. I therefore don't also want x and y to be inputs. It gives me the creeps, right? As should you too. Here, no problem. X, Y, and Z are the outputs. I am not using X, Y, or Z as inputs. I'm using 2 other variables. Arguably, it's better to leave it as it is because, after all, phi and theta mean something geometrically. And when stuff means something geometrically, it's nice to leave that conveniently accessible, visibly obvious for, your mental convenience. Yeah.
So, over here, we're leaving rho, phi, and theta as is because our outputs are x, y, and z.
Phi and theta.
Phi and theta.
Yeah.
So, can we, if we were to parameterize in terms of rho, phi?
No, so parameterization always means rectangular position as a function of parameters. Yeah, it's got to be rectangular position. Yeah. It's a good question. Okay. All right. Now this next tool is this is sort of a surface equivalent of y'all remember the bicycle wheel example that we did way back when, right? So how do you use vector algebra like in the bicycle wheel example when you're parameterizing a surface? And I came up with an example. It's a little bit weird. It is, in fact, fairly obscure. I haven't experienced this particular tool used very much, but I think it's a healthy read, and I hope you give it a chance. And the big idea is to realize that if you have, again, some surface, it might, in some cases, be easier to identify a point on that surface as a sum of something else that maybe is easy plus something else that maybe is easy. And in this case, if you want to read the details, go ahead. But basically, it's easier to get your hands on purple points by first writing down the green and then writing down the orange and then adding them. So a little bit obscure, not a good choice given our time constraints. Take a look if you like. This one is, I think, really important. There are a lot of situations that this comes up. I have used this in my, day-to-day natural experience taking physics classes long ago. So here's the big idea, and that is sometimes what you're going to want to do is to create a coordinate system. So, for example, suppose I look at this big donut here, known as a torus, by the way. And I want to parameterize the surface of the donut. I want to parameterize the torus. How do we do that? It's not a graph. Can't use the graph parameterization. Well, here's what I think is a good trick. I think this is a great choice. It's not the only way to go, but it's going to be hard to beat. And that is, let's pretend like this is the surface of some weird planet that we're going to, try to get humans to live on, or some space station maybe that we're building, right? Whatever it might be. And I want to be able to describe locations. Whoops, wrong color. I want to be able to describe locations. How would I describe the location of that point? And I could use X, Y, and Z, I suppose, but gosh, that's inefficient. And worse, how do I look at an XYZ and tell with any certainty, without going to a huge amount of trouble every single time, if the X, Y, and Z are even a point on the surface? Right? This is a bad idea, right? The much better idea is to agree upon some point to use as a starting point. I would suggest a point on which you might call the equator, sort of going around like that, and define coordinates. S is going to say, T is going to say how far do we sort of roll upward, like that, from the from the center of the doughy part of the donut there, and then S will say, okay, and then how much angle do I sort of rotate around the z-axis, sort of along the donut, and it's sort of a longitude and a latitude thing. I think that's a very reason. If we were building a space station, I think it's going to be hard to argue. I mean, this is how they would keep track of where you are in the space station. And we're actually kind of done now. I mean, because if you think about it, what we have here is we are describing position in space as a function of two parameters. That's what a coordinate system is. And that's also what a parameterization is. So, really, really nice trick. Again, I've used it a million times. Now, there's some geometry left to be done. I do have to do the geometry to figure out, okay, where is that purple point? And the process I would recommend on that, in this case, would be to start by writing down the coordinates of that point. I'm going to call P. That would be sort of this point here, right? That's geometry. Y'all can do that. Make sure y'all can do that. Trig, etc. Right? So follow through the details. Think about the vector addition aspect of what's going on. Make sure you're good. And then, here's the other thing. I already know how to rotate, right? If I want to do a rotation around the z-axis, well, rotating around an axis, done it a bunch of times. Now again, reminder, that is using a lot of linear algebra tools, and hopefully everybody's got that all solidified at this point. But if you don't, come on into office hours. Let's talk about it. I want to make sure everybody can do this comfortably. I am going to assume on exams that you're good at this kind of thing. So anyway, the point is, here's your rotation, and it's all over but the shouting at this point, because I've gotten a formula for that orange point P, and I know how to rotate. That's that matrix R, and the point we're looking for is literally the blue rotation of the orange point that I wrote a formula for, and multiply it out, and this is what you get. So again, details. Again, check through, make sure you're good with that. By the way, what you will find, if you look through the book again has a bunch of examples. The book presents this almost exact same example backwards. The book starts with, hey, what is that thing? Right? And then sort of makes a different argument, but concludes that it's a torus. And again, that's a cool example and I like it, but in practice, when you're going to need it, most of the time, the parameterization is not what you start with. It's what you need to figure out. Yeah?
Could you scroll up once?
Okay. If I can find my little cursor, yeah.
The point A, is it on the torus or is it inside?
The point, there is no point A. A is just sort of a radius. A is what you might call the bigger radius, right? And then B is what you might call the smaller radius. Yeah.
So it's on the inside edge of the torus.
It's a distance. It's not a place. It's not a place, right? So A is the distance from the center of the torus to the center of the doughy part that you want to take a bite out of.
Okay.
It's that distance right there. Yeah. Okay. Okay, so check through those details. Make sure you're good. Here's another really great trick. Again, I've used it a billion times, right? And that is to take some existing parameterization. Now let me just dive right into the example. I already know how to do a sphere, aka there's the rectangular equation. Here's the spherical equation. Notice it's a spherical graph, so it's easy to write down the parameterization. That's just spherical graph parameterization that we talked about a couple minutes ago. Well, here's the same thing written out one equation at a time. So the big idea, if you have an existing parameterization and we want to figure out, okay, here's a new, I want to parameterize not this equation, I want to parameterize this equation. That's an ellipsoid instead of a sphere, right? It's not the same. But, I mean, you know, algebraically, I mean, you see it's super similar, right? And I can see right here that, look, all I'm doing is everywhere I have an x, I've replaced with x over a. And we know what that does in equations. We know that that stretches things out, right? In the x direction by a factor of a. Likewise for y and z. So what do? How do you then deform the existing parameterization? Well, it's exactly what you would expect. Everywhere you see an x, you replace it with x over a. It's kind of the same thing. And then likewise for y, likewise for y, and likewise for z. So, hey, you know, again, you know, pretty cool trick. Now, here's a different take. Sort of a different take is to say, well, look, I can solve for x, y, and z in these equations. And if I did solve for x, y, and z in those equations, that would give me x, y, and z are this formula. So you can write that down. It's just a different way of writing down the same thing. And now here's the different take, though. How should I think about the deformation having happened here? Where's the deformation? Well, notice I'm literally taking my previous formulas for x, y, and z, and the deformation I'm interested in, well, I already know that I'm trying to make the x coordinates a times as big. And so look what I did. I literally took the formula that produces my x coordinates and I just directly, bluntly made them a times as big. Now, there's a source of confusion here. It's easy. Wait a minute. How do you know when to divide and when do I multiply? Right? It kind of looks like I multiplied here. Kind of looks like I divided there. Well, yeah, you got to keep it straight. Right? So take the time as necessary to think it through and make sure to distinguish between what you do to a formula for a variable versus what you do to where the variable sits in some equation. Right? These are different. So you just got to kind of think it through, and once you've kind of thought it through, yeah, okay, all right, it's the same thing, different take on the same idea. But anyway, okay, all right. This next bit, this is in the book. The purpose of this discussion, you'll notice, not going to be covered in class, so this is for you to read. The purpose of all this stuff about coordinate curves is to give a sort of a derivation of this formula down here for this thing called the capital N vector. You can take a look. I think it's a pretty straight read. You do have to kind of think through some details, but this is a healthy exercise. And that's if you want to know where this capital N comes from. And again, that's what we're skipping over here is the kind of stuff that I find the most fun to talk about. But when we're in a rush, we don't have time for, my fun, right? We got to get to problem solving and what are y'all going to need to know in your experiences. So the big punchline is that this vector right here this vector is the thing that when you look at an input area and its resulting image, little output area, this vector, whoops, wrong color, this vector right here, that's the thing whose magnitude, and it is important that we take the magnitude of it, that's the thing whose magnitude is your stretching factor. Now, we've used stretching factors several times, right? We used it when we were talking about change of variables. It's sort of the big point of view on change of variables is how much does the change of variables function sort of stretch things out. And then we did the same thing when we were talking about scalar line integrals. Basically, you're stretching out little pieces of interval. So this is, again, more of the equivalent kind of thing, except here what we're doing is we are stretching out little pieces of area. And you can probably see where this is going. Once you know how to do that, then you can do a pullback. And in particular, this is going to be a big thing for us, we're going to be looking at integrals defined on a surface. We're going to chop it up, add it up on a surface. We're going to want to be able to compute that. And to do so, we're going to pull back to create integrals that we can compute that are just good old double integrals. All right, so this is the big punchline, is this capital N vector right here, and I've repeated just to be bluntly obvious about it. Look how compact then our formula for our stretching factor is. Wrong color again. The area stretching factor is the magnitude of that capital N vector. All right, so let's do one. Real quick terminology. I like to call this thing, the capital N vector, I like to call it the parametrized normal vector, because that's where it comes from. Look at the formula, it comes right out of this parameterization. You have to have a parameterization R to be able to compute N. And furthermore, this N is entirely determined by the parameterization. When you parameterize, when you create a parameterization, when you choose a parameterization, you are imposing a choice. Capital N then becomes, it is what it is, it's computed by this formula. Now that said, it's always kind of bugged me a little bit, but the textbook calls this the standard normal vector instead of the parameterized normal vector. Okay, it is a standard formula that we use to produce it from a parameterization. But I feel like it makes it sound like it's standard to the surface itself, and it's not. It's not intrinsic to the surface. It is intrinsic to the parameterization, and that distinction is going to be a really big deal momentarily, like 10 minutes. Right? So, anyway, heads up, you're going to see that term standard. I'm going to use the term parameterized. And by the way, in my many years, I've never had a problem by not using that term standard. So I don't think you will either. Okay, all right, so let's see a quick example. We're going to compute the area of the unit sphere, and the very first thing I'll write down is this, that if I want to compute the total area, I'm going to take the sphere and I'm going to chop it up into little pieces of area ds, and I'm just going to want to add up all those little pieces of area. And of course, some little piece of area on the sphere, we already did this up here, some little piece of area on the sphere is going to relate to the pullback area by way of a stretching factor for which we have a formula. So we're going to kind of, prepare for this obvious need. Of course, we're going to need to know our area stretching factor by focusing first on what is that area stretching factor. And it's a straight up plug and chug. Parameterize, take the appropriate partials, compute the cross product. A lot of details in there. Y'all are real good at trigs, and y'all are real good at algebra, so make sure you can do all of that, right? Parameterize, take the partials, take the cross product, and then don't forget to take the magnitude at the end. And amazingly, all of this trig, and by the way, this is just the highlights. Going through the process of writing down, taking this cross product, it gets ugly for a bit there before it simplifies down to this. And then this process, you notice I neatly and conveniently kind of swept under the rug. How does that magnitude computation work? And you've got to do a Pythagorean magnitude computation on, oh my gosh, the trig just goes everywhere. Everyone should do this once in their lives. Again, I've done mine. It's your turn. Give it a try. It's just trig. No big deal. The Pythagorean identity comes up several times, like 3 or 4 times. And it all simplifies down to sine phi. It's pretty wild. So make sure you can do that, and then look, it's all over at that point, right? I mean, there's our plugging in the stretching factor, and if we're on the unit sphere, well, the unit sphere is described by, well, theta goes all the way around, and phi goes from 0 to pi. That's all the different possible places on the unit sphere, and easy integral. Nothing to it. And we get the familiar result that y'all probably all remember from high school geometry. Everybody good? All right, so a quick summary. There's very little new on this screen. I think it is kind of nice to have everything all together. And so again, here's our little input area. Here's our corresponding output area. You got to compute your various partials. Okay, I'll use dark blue for the partials. Their cross product is capital N, and the magnitude of capital N is the area stretching factor. Okay. So what is new on this page is just a little sort of computation right here. We got this formula, S partial cross T partial. Well, yeah, but if you just write out the position in coordinates, nothing happened there. And then if you just crank out the cross product, weirdly, unexpectedly, seemingly out of nowhere, notice when you take this cross product, those corresponding coordinates end up being two-dimensional change of variable stretching factors. What are the odds? It's very surprising. It's unexpected. Almost a little concerning. Okay. Why is there a two-dimensional stretching factor, change of variable stretching factor here? We're not doing a two-dimensional change of variables. So, turns out there's a great reason for why that shows up. And it's one of the many things that, I just have to confess we don't really have time for, and that's more of a me having fun thing. And now, on the other hand, if you're curious, if you want to see what is the very reasonable explanation for why these are what they appear to be, great question for office hours. Come on in, I'd be happy to discuss. But it's not going to affect computations, so you don't have to know. But it's still cool. Okay, here's a nice special case. Sometimes you're looking at a graph. And when you are looking at a graph, sometimes you will choose to use the graph parameterization. And when you do use the graph parameterization, notice that your partial derivatives will always compute out the exact same way. And your cross product will always will crank out the exact same way. And the magnitude of that will always, therefore, look exactly the same. So this is a nice little streamlining, and I encourage everybody to, take note. And if you are using a graph parameter, specifically a rectangular graph parameterization, and everything's going to play out like this. You don't need to go through this song and dance every time. Just boom, just cite this formula. It's fine. Right? All good. So you should memorize that formula. But I cannot emphasize enough that if you're using the graph parameterization, and you cannot assume that you always will. In fact, you will absolutely, in some cases, be unable to use the graph parameterization because your surface isn't a graph. Or even if it is, you might have other reasons not to want to use the graph parameterization. So this is a secondary alternative special case. What you have to know is the general formula that the stretching factor is the magnitude of capital N. That's the main thing. Okay. All right. Now there is a fun. I think this is cool, and this is quick enough that I can rationalize doing it. Oh yeah, go ahead. I'm sorry.
So how did the FSFT set squares?
Yeah, because X and Y are S and T. Yeah, and so this is what I write when I'm sort of doing the full thing and I'm thinking in terms of an actual parameterization and a pullback. And this down here is what you write if you're kind of trying to avoid all that in the first place and just leave everything in terms of X's and Y's. Yeah, absolutely. Yeah. Okay, so neat special case of the special case. Notice that this is the magnitude squared of the gradient. How about that? What are the odds? And don't forget that the magnitude of the gradient tells you how steep your graph is. So this is a nice alternative rewrite for your stretching factor in this graph case. Your area stretching factor, when you're looking at the graph parameterization, entirely a function of steepness. And I'm going to show you a very real-world practical example of how you can use this. Suppose you have a house. Someday you may have a house. And that house will probably have a roof. That roof will probably have various sort of polygonal components, you might say, pieces. It comes in these chunks, like so. How are you going to compute the area of that? Right? I guess you could get up on the house and measure, but first of all, please don't climb up on top of your house. You fall, you break your legs, right? Or worse. Please don't. Just, oh my God. So yeah, you got a problem if you want to compute that area. No, real quick aside. Okay, how about who cares? How about we just don't? What do you need to compute the area? Someday you may need to put a new roof on your house. And just FYI, those cost in the 5 digits very often. Bonkers expensive. And my experience, I'm just saying, right? My experience has been that when I'm spending big bucks, there's a oddly consistent tendency for whoopsie doodles in the calculations that always go in the favor of the contractor. It's just weird, right? I'm not accusing anybody. I'm just saying it always goes in favor of the contractor. Isn't that strange? So I'm a double checker, right? And by the way, I saved myself $5,000 one time because I double checked the math on the mortgage calculation, and they whoopsied $5,000. And I never would have caught them if I didn't know how to do that calculation. So thank you, single variable calculus. I've caught various other mistakes along those same lines. And then I started telling contractors, by the way, I'm a mathematician and I'm going to double check all this stuff. And then weirdly, they don't make mistakes anymore. So this is good stuff to know. So, how am I going to compute that area? Well, the big idea is to say that, in fact, that is a graph, and it's a graph sitting over the footprint, and the footprint is easy to compute the area of because it's all right. Well, I mean, maybe rare exceptions here and there. great majority of houses, the footprint is just make up a rectangle. The world's easiest area calculations. You can measure all the relevant dimensions with a tape measure. You can't fall. You're already on the ground. It's really easy. Okay? And so, well, then I can just argue that to compute with a pullback, I need to relate how much area I have there with the corresponding little area of the footprint. The area of the footprint is a dx dy. And I get the corresponding area up there by multiplying by the stretching factor. And I can measure that stretching factor by understanding the steepness, and I can compute the steepness like going into my attic and picking any rafter, right, and just, put a rope with a little weight down there and make a little effective triangle and a level. And it's no big deal, easy calculation to find that steepness. And so you can measure the area of your roof pretty accurately. Right? And it might not account for, the overhang, how far does it hang over, or maybe they have to overlap a certain amount. So certain things you can't do, but you can get it accurate within 1%, and that's good enough. So, anyway. I think that's a cool calculation. Okay, moving along. So that was 7.1. Hopefully we'll get 7.2 done today as well. We've already got the big ideas, the groundwork pretty much already laid. And that is, if we're looking at a surface, here we were looking at a sphere, just an example of a surface, right? Here was our picture. If you have some sort of a surface, and if you maybe you want to do more than compute the area. Maybe I want to compute the total. Let's just go with population, right? So maybe there's population distributed over the sphere. Maybe this is planet Earth, and we're talking people. Maybe it's a ball that has mold growing on it. I don't know, whatever, right? And you want to do a chop it up, add it up. You're not computing areas, but you need to take an integral where you're accumulating over a surface and pull it back to some sort of, computational tool that you can do as a double integral. And so we just need to sort of admit that, this is a new kind of Riemann sum. We are adding up over a surface. Let's see here, adding up over a surface. And on each little piece of surface, we're going to multiply some sort of stuff per unit area times area. Stuff per unit area times area gives us stuff, and we're just adding up the pieces of stuff. Now, I like to point out, this is just like we did when we were looking at scalar line integrals, right? Scalar line integrals was a curve on which we were doing a chop it up, add it up. But same basic idea, we've got this weird domain that's all curvy and stuff. Surface. Don't like it because it's all curvy and stuff. Chop it up into little pieces, same. And just recognize that on each piece there's going to be some notion of stuff per unit size to multiply by size. We're ripping off morally the same idea here. It's just area instead of length. Everybody buy it? Okay, so again, we borrow notational ideas. I think this is all pretty straightforward. And do notice that we are specifically calling this a scalar surface integral. Same reasons as before. It's because that is a scalar and that is a scalar. And reasonable question, well, what else could it be? And what we're going to find in a couple of minutes here is that, there's going to be a case where it turns out those are vectors. That's just a little foreshadowing. For the moment, let's leave everything scalars. And so the next looming question is, how do I compute these things? If I want to do a chop it up, add it up on a surface, how do I pull back to produce, hopefully, an integral on a nice, pretty domain in 2 dimensions, 2-dimensional domain in a 2-dimensional world? It's a good old-fashioned double integral, but I know we're experts in how to compute double integrals. So how do I turn this brand new, mysterious, hard to get our hands on kind of an integral into something that I can actually work with? And it's the same idea that we saw with curves. We parameterize, and then we pull back through. Whoopsie, wrong color again. And we pull back through the parameterization. And again, the stretching factor, right? The difference between input area size and output area size, that stretching factor we already know, right? We just got through computing the thing that you multiply by input area to get output area. And notice that's all that's happened down here. I just insert that stretching factor when I say, get the colors, that ds is stretching factor, right? That stretching factor times, my thing died again. Oh my gosh. Times input area ds dt. We already had it, okay? Conveniently, lucky break. So we, in some sense, already knew how to do this. Everybody happy? Pretty sweet. Let's see here. Oh, you know what? Give me a second to plug this in. Hopefully this will charge up. Okay, again, slight concern. This seems to depend on the parameterization. If the integral depends on the parameterization, doesn't its output value, what it computes, depend on the parameterization? Wait a minute, it shouldn't depend on the parameterization. We're trying to compute something that's actually on the surface. We made up the parameterization. So should the parameterization matter? Thankfully, it turns out that it doesn't. Parameterize however you like, all good, no problem, won't make a difference. And the book proves that, but that's not the course we're taking. Okay, so here you go. By the way, you'll notice, again, a pattern. I'm going to show you a bunch of examples, all based on one surface. And we're going to, mass distributed over the surface. And we're going to compute various things, like what's the mass, what's the center of mass, what's the moment of inertia, blah, blah, blah. So, first step, parameterize. Right? We're looking at the unit sphere, a specific part of the unit sphere, but anyway, that's how you parameterize. Yada, yada, yada. To compute the stretching factor, we already did that. We did that at the end of 7.1. Right, so, again, make sure you can do that calculation. Comes up to be sine phi, as it turns out. And then it's kind of all over with the shouting. It's just a matter of plugging in. So, for example, here is the integral I would use to compute mass. Whole is the sum of the parts. And then one little bit at a time, we use, sort of shorthand notation. Mass is mass per unit area times area. That area is stretching factor times input area. And then again, it's just a matter of kind of plugging stuff in. That's right. We've already computed our stretching factor. Right. Don't forget, so easy to forget, but don't forget that the parameterization itself is telling us how to plug in for our various variables. So that's the formula for z. So we literally plug that in there. And then likewise, this is the formula for x. Right? So in this other calculation, that's how you know how to do that. It's very plug and chug. Is everybody happy? All right. Okay. Make sure to read through the rest of the details on these examples. I encourage you as well, read through all the details on these two examples, which you're going to notice very quickly, it's all kind of the same. Right? But make sure that you are very comfortable with how it's all kind of the same. Okay. Okay, next example. By the way, let me go back real quick to, I'm sort of losing track of where I wanted to be. So let me, let's think back to this next example we did with line integrals. We computed various scalar blah, blah, blah. Now we're going to consider work. And remember something strange, something different, something fundamentally different happened when we consider the work question. For one thing, we just have to recognize that this old formula doesn't work anymore. It assumes we have constant vector field and a straight line path, and that's not real world. Vector fields tend to be non-constant. Paths tend to be non-straight. That's the way it is. And the direction matters now all of a sudden. Right? The amount of work it takes to drive up a mountain road, very different from the amount of work it takes to drive down a mountain road. Well, okay, so kind of same things going on over here. Now, it's not going to be work. Now, it's going to be flux that let me zoom. There we go, that's much better. It's going to be flux that we're going to compute. This is just kind of what leads most conveniently, I think, to the answer we want. Why do we care about flux? Well, because it computes natural things like volume per unit time of flow rate or mass per unit time of flow rate, depending on how you write your vector field, right? So, various different ways in which flux is interesting, but it remains, whichever one of these you're interested in, I don't care. This formula is interesting. This formula computes cool stuff. So how we compute flux is an important question, and recall that this formula assumes that you have a flat surface and that you are looking at a constant vector field. Because that's what we did when we were back in chapter 3 when we derived this. So we're in the same boat again. We have this important idea. We only know how to do it in the special case of constant and flat and, sort of best case, easiest case scenarios. And now we're going to have to figure out what happens if we have a non-constant vector field and a non-flat surface. Oh, and here's another thing that's tracks, and that is all of a sudden the direction matters, right? Because we want to know in a particular direction through the surface, right? We have to recognize there's a difference between fluid flowing that way through the surface versus fluid flowing this way through the surface. Those are pretty different things. So how are we even going to indicate what we mean by what is these are opposites. I need to designate one of them as being the positive direction through the surface, and we do that with a normal vector that we're going to call an orientation. So here's the big idea. Again, you got to decide what is your positive direction through the surface. That's what's going to define for us something called an oriented surface. So the oriented surface is the surface itself with an understanding that that's, as indicated by N, what we mean by the positive direction through that surface. Quick reminder, don't forget, that was one of the first things we did over here. We talked about what it means to have not just a curve, but an oriented curve. So we're just stealing, we're just copycatting from what we've done before. Okay, and yeah, we chop it up into little pieces. For example, right, we'll look at little pieces like this. That's approximately flat. Nice and small, so the vector field is approximately constant. Again, on the small scale, things tend to be nice. Right, so we're going to look on the small scale, some little piece. And on that small piece, everything works out nicely. On that small piece, again, it's approximately flat. Got our normal vector. The vector field is approximately constant. And there's our old news, chapter 3 formula for how to compute the amount of flux happening on that teeny tiny little piece where all of our assumptions basically fine. Is that cool? And then, yeah, so you add them all up, right? So this amount of flux of that vector field through that little piece of surface, add up over the whole to get the whole, and this formula, plug it into there, gives us something that we can compute with. And do notice that this thing we've ended up with here, it kind of looks like a scalar surface integral, right? We've got a integral over a surface, and the differential appears to be ds, just like before. But we know that can't be really, honestly, what it is, because we've already noticed, hey, look, orientation matters. Orientation doesn't matter when you're talking about area. Orientation doesn't matter when you're talking about how many ants are crawling around on that thing. Right? It doesn't matter what direction you add things up when you're talking about those kinds of objects. But here, which direction through the surface all of a sudden matters. So we know something is still different, and this notation here is hiding it. Right? So I'm going to fill in just as a reminder, when we were computing work, right, we were adding up little pieces of work, and the very first thing we wrote down, sort of chronologically, it went in the other order, but we say, okay, we're going to add up over the curve f dot dr. That was our first thing to write down. And then we subsequently observed that you could rewrite that as an integral of f dot t ds. And we made this observation that well, look, this thing right here, TDS, is just kind of a different way of writing the dr vector. It's just breaking down the dr vector into a direction and a magnitude. Right? Direction and a magnitude. Specifically, what unit vector describes how my little piece of curve is oriented? So orientation times, and then the size. What is the size of that little piece of curve? Well, check it out. We've got the same thing here. If you look at that n and ds, that's the orientation. That's the unit vector describing our orientation, and that's the scalar differential telling us the size. Now area instead of length. And so, noticing that very strong similarity, I think this is a great notational choice. Little n ds, d big S scalar, we're going to rewrite as the ds vector. So this is just kind of piggybacking off of this old idea. This dr vector is very natural. It makes loads of sense. It literally represents a displacement along a piece of curve. We subsequently make the even happier realization that this tells you everything about your little piece of curve. And likewise, the ds vector. It's telling you everything you need to know about your little piece of curve. It's got the size, it's got the orientation, all built in to that ds vector. And I think this is the much better way to think about vector surface integrals. We are in fact computing something different. It should look different. And as promised, notice our differential is now a vector, and our integrand is now a vector. Everybody okay with all that? Okay, cool. How do we actually compute these? Again, we already know. We already got everything we need. It's just a matter of sort of observing that, yeah, it all fits. So, real quick, here's our reminder. We've written all of that down previously. Got a parameterization. Position on your surface is a function of your parameters, S and T. We know how the area stretching factor works. We know the capital N vector is the thing whose magnitude is the stretching factor. By the way, we also know that the capital N vector is perpendicular to the surface because these partials are tangent to the surface. All right. Here's our vector surface integral construction we wrote down on the previous page. That's just a recopy also. I just wanted to have it all right here together. None of that's new. And we make the one little quickie observation that if you take this formula, put that in there like that, then check it out. Our capital N vector seems to just show up. And now, okay, where did that come from? I know that this is capital N. Well, if you think about it, the little n points perpendicular to the surface, just like capital N. This product has magnitude, which is magnitude of capital N, which is likewise the magnitude of capital N. Right? So this product, little n times the magnitude of capital N, this product has the same direction, it has the same magnitude as capital N. And as I like to joke, if it looks like a duck and quacks like a duck, doesn't that suggest it's a duck? What do you think? Is everybody following? Yeah. Now, mea culpa, I did just commit a math crime. I did it on purpose for dramatic reasons. Well, for two reasons. Partly for drama. Right, so I'm going to confess what that crime is. Right, so my assumption that that's equal to that is going to turn out actually not going to be quite true. And I want to let y'all wonder for a bit about why would dumb things that look like ducks and quack like don't they have to be duck? It's very tempting, right? The other reason I'm not going to correct my crime right here and now is because there's a lot going on. Right, we're processing a new idea of a new kind of Riemann sum. Oh, it's too far back. We're dealing with orientations and flux, trying to remember why flux matters. New kind of application of our surface integral construction. We haven't even computed one yet. We haven't even gotten a victory under our belts yet. There's a lot going on, and I don't want the distraction for the moment. So for the moment, I'm going to sweep my crime under the rug, and I will come back and fix it in just a bit, like 5 minutes, or less, very quickly. Okay, that said, this is kind of the big punchline right here, and that is that if you want to compute flux through a surface, this is a plug and chug formula that will do it. If you have parameterized your surface, notice that all of this stuff I can write in terms of the parameterization. S and T are our parameters. N is computed from the parameterization, which is also in terms of our parameters. F is in terms of X, Y, and Z, but those are parameterized and therefore functions of the parameter. All of this can be pulled back and written in terms of the parameters. And that's how these computations are going to go. So here it is, first example. we've got ourselves a surface, and we've got ourselves a vector field, and we want to compute the flux. So I'm going to cite the formula that we just got through looking at. Now, okay, wait a minute. That formula requires us knowing this capital N thing. Okay, so we do have to do the same song and dance we always have to do. When you're doing a surface integral, the plow forward direct way of computing a surface integral is to parameterize, take the appropriate partials, do the appropriate cross, and then I guess, we were kind of expecting to have to take the magnitude of that thing. I mean, that, in 7.1, you got to take the magnitude of that. It was scalar surface. I guess that was early 7.2. Anyway, scalar surface integrals, you need to compute the magnitude of that thing. Notice, here we don't. Here, it's just literally in itself. You don't have to compute the magnitude. Now, that does seem uncomfortable. Hey, shouldn't the magnitude be in there? Well, it is. There it is. The magnitude's in there. You just don't have to compute it explicitly because it's already factored in. Does that make sense to everybody? This creeps some people out, myself included, when I was y'all's age. Okay. So, boom. So it's a pretty straightforward calculation here. You'll notice that I'm just going to take my formula for N here and just stick it on in there. Notice also I am plugging in for my vector field. Let's see, how did the vector field here turn into that? Well, Z. Right there. Right, just plugging in from the parameterization. Everybody see how all I'm doing in this step right here is just plugging in. All right. Yeah. And while we're at it, I'll go ahead and point out it says. Right here, above the unit square. Above the unit square means we're looking where at, the part of the surface where x and y range over the unit square, which means that s and t range over the unit square, which means that the bounds for s and t are the unit square. Now it's chapter 5, double integral. Off you go. Nothing to it. Everybody okay? Okay. All right, so it's confession time. What did I do wrong here? What is the crime here? Let me see if my old stylus is back in business. Yeah, we're back in business. Okay. All right, here it is. You got to worry about orientations. I totally swept that under the rug. And I will point out, for your consideration, a lot of y'all probably didn't notice. And it's because it's really easy to not notice. It's super easy to just doesn't leap off the page at you that you may or may not have oriented correctly, right? But keep in mind, when a question is asked, the surface comes with an orientation. You've gotta, if you're gonna say, I want to compute the flux through a surface, you've gotta tell me, as part of the question in some way or another, it has to be unambiguous which way is the positive direction through the surface. And I didn't pay any attention to that in the calculation that I just did. I just said, you know what, let's parameterize. That parameterization will determine these partials. That will determine this cross product, which will determine a basically random orientation based on how I kind of carelessly and randomly parameterized. And no fair. Right? You can't just assume that your orientation is correct. And again, here's exactly where the crime happened. So we found ourselves looking at this expression right here, this having been the orientation unit normal. That's where it came from, right? This little n right here came from, I was just writing down the formula for flux, and flux depends on how the surface is supposed to be oriented. So that's the orientation unit normal. But when I parameterized, right, my capital N is what determined what I wrote as little n there. And that ignored the orientation. So when I made the claim, again, I made this claim that, that's the same as that. I was assuming unjustifiedly that I parameterized the correct way. And it's coin flip, you might not. Everybody see the problem? Now, again, for analogy purposes, I think the analogy is good here. If you go back and think about the analogous question here, right? We talked about back with line integrals that, hey, you've got to parameterize the correct direction. If you don't, you're off by a minus sign, and you'll get wrong answers to the tune of a minus sign. And we realized that you can actually kind of use that to your advantage. You can parameterize wrong on purpose, and then just fix it with minus sign. Right? And we talked about that with this example down here. Right? This was the much better way to solve that problem. But all of this was kind of capitalizing on the fact that which direction you're parameterizing is pretty obvious. Like you parameterize this thing, you write down there's your t, and of course I'm parameterizing clockwise because, that's why I define t to be this. You can just look at your picture and see which direction you're parameterizing. That doesn't hold with surfaces. With surfaces, it's hard enough just to get any parameterization on the page, and there's so much work that you got to do, so much tedious algebra to figure out which way you can parameterize. You basically can't tell. You may have parameterized one way, you may have parameterized the other way. So that's going to be a difference that we're going to have to deal with. It's a little bit annoying, right? The problem that we're dealing with here was just kind of obvious over here. Not obvious here. So let me show you how to deal with this. Ultimately, straightforward. It's just, it gives us an additional step. Here's basically the same example we just did. The only difference, let me go back up to here. The only difference is you'll see when we did this example previously, it said upward. Again, for dramatic purposes, it kind of swept that under the rug. I don't know if y'all caught me on that, but I spent time talking about how to parameterize and how to do the plugging in, and I just kind of glossed over the fact that this was oriented upward. So let's see how we would have to deal with this if it says instead that it's oriented downward. And, here's how it goes. Our surface is oriented downward. I parameterize the same. I compute the partials the same. I do the cross product the same. I'm just kind of going through the calculation. And now, wait a second. Now I have my normal vector. And I can just visibly see this one's pointing somewhat upward, not downward. Right, so look, all you got to do, right, to deal with this problem is just remember that once you write down your capital N vector, just pause and step back. It's a very important little pause. It also gives your brain a little break from the tedium of calculation. But when you write your capital N vector, you need to pause, stop, step back, and say, whoa, I seem to have imposed an orientation on this problem that I did not think through. Because you can't. And you gotta just check and see, wait a second, did I do it right or did I do it wrong? And you can see here I did it wrong. And so you fix having done it wrong by saying, whoopsie, and then just sticking a minus sign to fix it. Problem solved. Is that cool? So pause after you make your capital N. Look to see if you parameterize the right way or the wrong way. If you parameterize the right way, cool. Just say, you can just write down on your page, parameterized correctly, smiley face. Great. Right? If you parameterize wrong, you can just say, whoops, stick in a minus sign. You do have to make it clear where the minus sign come from, right? Again, you always have to document your reasoning. I can't emphasize this enough. You all heard me say this a million times. It's just so important. Sticking in a minus sign with no justification, you can't do that, right? You gotta explain the reason. There is a pretty significant thought that leads to why we put a minus sign in there. So you gotta document just a little bit, right? I mean, what I've done here is plenty. You gotta give me a little something. And then the rest of the calculation, off you go. Same, pretty much the same. Everybody all right with that? Watch your language a little bit, not in the, I didn't mean it like that. But when you describe your orientation, you got to be a little bit careful about how you describe orientation. So here we were just looking at a surface that is like so, and so you can kind of distinguish between, that what I'll call blue orientation and this sort of, orange orientation by saying, well, look, check it out. The orange vectors are all somewhat downward. They're not perfectly downward, but none of them are in any sense upward. And the blue orientation are all somewhat upward and in no sense downward. So this terminology right here is fabulous for that surface. Upward and downward distinguish these two possibilities from each other unambiguously. There's no doubt what we mean by the upward orientation on that paraboloid. But that same terminology does not do a good job. I can get this to disappear. If I'm looking at a sphere, my two options, that and this, are both somewhat upward and somewhat downward. And so this terminology here is unacceptable. It is completely unworkable. Which one do I mean if I say upward? These orange vectors, half of them are upward. The blue vectors, half of them are upward, half of them are downward. So you got to tailor your language. The big idea to keep in mind is that we are not trying to give an exact description of the orientation. We got formulas for that, right? The purpose of language, the purpose of verbiage to distinguish between two or to describe your orientation, is to just remove the ambiguity of which one you're talking about. We know there's two choices. You just want to pick the language that removes the uncertainty as to which one you're talking about. It does not have to be exact. And the flip side of that, by the way, is that if an orientation is described as upward, that does not mean 001. All we're doing is removing an ambiguity, and you can see it right here. Check it out. Those vectors are not all straight upward. Okay. Oh, shoot. I am kind of out of time, aren't I? So, okay, we'll draw the line right here. We played some good catch-up ball. I think we got a lot of good stuff done today. But we are out of time. We'll pick up here tomorrow, and we're going to continue to play catch-up ball. All right, see y'all later. Have a good rest of your day.